If not, then I plan to do a little bit of more of microcanonical ensemble and go on with where I left last time, but maybe not the whole of the tutorial session. Oh, I did not even probably start. I haven't started. Okay. Okay, I haven't started. Okay. I forgot what. Where did we start? Oh, acha. We were doing this Liouville's theorem. I think. Acha, yeah. So this microstate and this thing is clear. Like many people had doubts about. Okay, so I can give you like another example. So whenever I write n, n is the degrees of freedom, number of particles, whatever. So don't think of n always as 10 to the power 23. I mean 10 to the power 23 is the number that we will eventually be dealing with in statistical mechanics, but to understand concepts one doesn't have to always think of 10 to the 23, n could be 1 or 2 also. So one example that I thought of was, so think of quantum mechanics. Now you have, let's say you have two spins, two spin-off particles, they can be either up or down, and suppose you are told that the spins can be either up or down, okay, and so there are two of them, and we are told that the total magnetization, which is the sum of the spin components, is 0. Okay, so this is a macro state. So I told you that there are two particles, total magnetization is 0. Okay, so there are n is equal to 2 and n is equal to 0. So can somebody tell me what are the, so this is the macro state, let's say. So can somebody tell me what are the possible microstates? Is there 1 or 2 or how many? 2 microstates. 2 microstates. So the microstates. So number 1 is, so let's say, so I have spin 1 and spin 2. So the 2 microstates are spin up, spin down. This is 1. The total is, so it is consistent with the given macrostate. Also this one. This is also consistent with the given macrostate. So this is also a possibility, but it's not consistent with the given macrostate, and so is this one. So the collection of all microstates consistent with the given macrostate is referred to as an ensemble. And like as I mentioned many times in Carson-Wang, they say that these are identical copies of the same system, identical systems or something. I think one should not get into that. I think it's a bit confusing. System is just one system of two particles. It may exist in different microstates. Well, you can think of them as identical systems, but if it is too confusing, you can forget about it. Like in Carson-Wang, they say identical systems, but system is one. So some people get, start to think of them as separate systems. One is here, one is there, but it's not. A system is this piece of chalk. This exists in a given macrostate, which is the length and the temperature and volume and susceptibility of this piece of chalk. That's a macrostate, because when I specify the macrostate, I don't tell you what the positions and the momenta and everything, every microscopic detail of this piece of chalk is. So all microstates which are consistent with a given macrostate is called an ensemble. You see, all the systems, okay, if you want to think of it this way, that's fine, but system is just one, a system of interest. It may exist in different microstates, and of course each microstate you can think of as a system, which is fine, there is no problem in that, excepting that I feel when somebody is teaching this thing, I mean one should be careful in making this distinction, that a system is a system. Now you may call a microstate also as a system, and then you have to say that, well, this system exists in infinite number of systems, something like that. I mean, with just I think it is not needed. I mean, if you are clear about what it means, then it's fine. But usually, this is my feeling. I don't know. Like, should one really invoke this concept of mental copies and this? I mean, it's just a given macrostate corresponds to many microstates, and that's it.
Many people have done that. That's why
Yeah, many people are, so we will not do that. Let's put it this way. Maybe, I mean, there are things.
Ensemble is an easy way to get an idea of probability. I mean, in the sense that you have many copies of something, we call it system. Then looking at the number which have a particular microstate, because that number of objects might exceed the number of microstates. That number gives you a measure of probability. So people can visualize it.
No, but so the way I was doing was, so while introducing the concept of microstate, I haven't yet defined what rho PQT is. Just to introduce the notion, one doesn't always need to have this mental. You may have. It's just a question of what you are more comfortable with. Taste. Okay. Or it should not introduce more it should not be more confusing. If you know what you are talking about, because yesterday I found that many people somehow are thinking that these are like different systems. One is here and one is in Salt Lake and one is in Belur, something like that. It's not like that. It's just my system of interest, microstates, and that's it. No, so you are saying something. No, okay. Okay, so now you.
When we present those whole microstates in the place systems, there is gamma space. It is just a point.
No, every microstate, like for every microstate you have a point.
Ensemble will have
so many points. Yes, exactly.
That is clear.
Huh.
Now time evolution is
Okay, so let's get to that. So macrostate and microstate and phase space and representation of a collection of microstates, consistent with the given microstate by collection of points in the phase space, as he says, these are fine. So this is my, this is my gamma space. Okay, so the coordinates, the axes are q1, q2 up to q3n, and then p1, p2 up to p3n. And so this is one microstate of the system, and consistent with the given macrostate, there may be many more. So you will get a collection of points, some collection. Okay. Now the question, so this is at a given time. At t equal to 240, I tell you that this is the temperature, this is the pressure, this is the volume, and therefore you think of all possible microstates that the system can have, which are consistent with the given microstate, and therefore at this time you plot them and you get a collection of points in this. Now what is going to happen as time passes by? So what is going to happen is that you remember that each such point has got 3n coordinate components and 3n momentum components. Now these points are going to move around in time. Each point is going to move around in time. How? That we know, because the system, the dynamics is governed by an underlying Hamiltonian. The Hamiltonian is telling you, so think of it this way, that there is a Hamiltonian. So forget about those points for the moment. So there is an Hamiltonian which is telling you how each of the 3n coordinate components changes in time, and that's according to this this law. And there is a set of another 3n equations which is telling you it is telling you how do pi's evolve as a function of time. Okay. So as the qi's and the pi's, their values change in time, this point is also going to move. Okay. You started with one microstate. Well, I say you started, but the system started being in one microstate. It moves to another one and another one and another one and so on. So for this particular microstate, this is your initial condition. You just let the system evolve according to these Hamiltonian equations. You get some trajectory here. If you remember in the part on dynamical systems, we were after this trajectory. We wanted to know how does this trajectory look like. Gamma t or something, some notation that I was using. So this is for our given microstate. Of course, if I start with a different initial condition, a different microstate, that is going to move around in some other trajectory. The rule is that two different microstates, I mean the trajectories corresponding to two different microstates cannot intersect each other. This we have discussed why it is so, because then these are first order differential equations. For every initial condition there is one final condition which is unique, and this point is going to move and that point is going to move. So ultimately what will happen is that this whole collection of points, you don't know how many they are and how they are distributed, but whatever they be, this whole collection is going to move in time. Okay, this whole collection is going to move in time, and therefore the density itself will change in time, and that's the quantity we were after. So rho pqt, if you remember, what we were doing was that at a given instant I ask, at a given point in this 6n dimensional space, the point is denoted by P and Q, or I was writing, I keep forgetting, should one write QP or PQ? QP, right? QP, so let's do that. Yeah. So let's do the standard thing. Because H also, yes. So if you remember, this Q is this whole set, Q1, Q2, Q3 up to Q3, and P is also this whole set. This is just a small. So what is going to, so what is this rho P, QPT? What I do is that at a given time, okay, at a given time I have a snapshot of the phase space. All these points are there, this point is here, that point is there, and so on, and they are distributed in some way over this space. And well, they will be distributed over the energy hypersurface, because we know that such a dynamics is going to conserve the total energy in time. So therefore each of the trajectory has to lie on the constant energy hypersurface. Okay. So how do I define that quantity? What I do is that I go to a point that has coordinates qp, I mean the full set q1, q2, p1, and what I do is that I just draw a small volume element around it, and I ask how many points are there in that volume element, and by definition that is equal to rho qpt dq dp, where dq means dq1 dq2 up to dq3 and dp1 dp2 up to dp3. This is at our given instant, and obviously at the next instant these points are going to move around. So therefore the density that I had observed at this location at time t is not going to be the same generally at the next instant. So there will be some time evolution, so that's why there is an explicit dependence on time, and there is also a dependence on q and p, because like even at a given instant, if I make my observation at a different point in the phase space, generally I will see a different value. Okay. Till now we haven't discussed equilibrium, what does equilibrium mean and so on. It's just I am trying to construct the phase space based on this thing that I have a Hamilton equations of motion and so on. Till now I haven't introduced the concept of equilibrium in the context of in this statistical mechanics picture. I don't even know what does it mean to have a macro state which is not changing in time. How do I measure a macro state, some observable in terms of rho qpt. I haven't defined all those things. I'll come to that hopefully today, not hopefully, definitely today with probability 1. So but so this definition is clear, right?
One minor point, the Q and the P standing as arguments inside rho, they are not moving according to Hamilton's equations.
Well, okay, so this is the thing that, okay.
People may, because
okay.
Q
Okay. So what he is saying is that, see, this is your observation point. You are staying somewhere. See, these Q's and P's, okay, although I am using the same notation in some careful textbooks, you will see this, the coordinate axis, they don't know which system you are, who are you, and which system you are dealing with. X axis is X axis for you and me and for everything else. So this Q's and P's, I think there is a name for it, that these coordinate axes, they are there, you are representing your system by a point in that coordinate axis. So QP is really your observation point. I mean, this is a point in the coordinate axis. It just so happens that at a given instant you find some points here, some points there, some points there, and so on. So as time goes by, what is going to happen is that you are making your observation here, and some trajectories will come in and will get into this small this volume element like around you. Some trajectories will get in, some trajectories will leave that, and that will lead to a change in rho. Is this point clear? Yeah, you can think of, so let me just draw this thing a big one, and become, so this is your observation point QP, and as time goes by there might be some trajectories that enter that region, or some points that leave, and so on. So I am just trying to see how does this, so this Q and P, these are not really generalized coordinates in that sense. You are representing your generalized coordinates by a point, generalized coordinates and momenta by a point in this space.
Coordinating 6 and dimensional space.
Yes, exactly, that's it, that's it.
So during this evolution of microstate,
Huh.
the macrostate is fixed.
Yeah, I did not say like anything about it. The macrostate may change as a function. So a particular state will be the state of equilibrium in which the macrostate itself will be time independent, and we will see that then it necessarily means that rho has to have a particular type of time evolution. I mean, if it has got explicit time dependence, then del rho del t has to equal minus of, I will come to that. I am just what I am telling you is the following, that at every instant, okay, some features of the macrostate remain time independent. For example, the total energy, that is not changing as a function of time. The total number of particles, well, the total the net volume of the system, but it may so happen that there are observables that is changing as a function of time, and that goes into defining the macrostate. Let us say the magnetization is changing. I still have 3 particles, I still have temperature equal to 10 degrees centigrade or Kelvin, I still have 2 particles, 10 degrees centigrade, but maybe the magnetization is changing as a function of time. But at every instant, the point is that at every instant, given the macrostate, I can construct the microstate, this picture in principle, and I can look at how does this guy change as a function of time. So we will see that a state of thermodynamic equilibrium is one in which all observables have time independent values, and that would put some condition on this rho QPT. So let us just, I will not do this derivation because this derivation is rather simple, but just I will just tell you how does rho change as a function of time, and I think you are convinced that rho has to change as a function of time because the trajectories are moving around. Or maybe I just indicate how does one. So what you do is the following, that in this 6n dimensional phase space, you consider like an arbitrary volume, okay, some volume omega. It does not have to be infinitesimal. So there is an arbitrary volume. This is an arbitrary volume in this 6n dimensional phase space, and then one thing is for sure true, that the number of microstates is not going to change as a function of time. The number of microstates which are possible with the given macrostate is not going to change as a function of time. That means the number of points that you have, the number remains constant in time. No new microstates are created, nor are the existing ones getting destroyed. Okay. So then it then means that if you have some volume omega, and in a small time delta t, if you see that there is a net decrease in the number of points in this number of microstates or phase space points in this volume, it just means that there has been a net flow of points out of it. It could not just happen that in a small time delta t the number came down because some microstates disappeared. It's not possible in this setting. So therefore, what will be the total number of microstates or the total number of phase space points which are contained in this volume will be by definition. So what I have to do is that this rho QPT, rho of QPT, so dq dp, and I integrate it like over this volume. So and I take ddt of that. So, that is going to tell me what is the net change in the number of microstates contained in this, and if it so happens that the number decreases, that means there has been a net flow of points out of it. Some points have come in, some points have gone out, but definitely the number of points that have left is larger than the number that has come in. And so, how do I compute the number of points that have left this thing in unit time? Yeah, because I am doing ddt, that means in unit time, right? So, that's what it means, that in dt time so much have gone out. So, ddt means in unit time. So, in unit time, so I have this, so I have the picture even there. So, suppose somewhere on this surface, so this is a volume which is enclosed by a closed surface. So, somewhere on this surface, if this is the unit vector, so how do I compute, how do I calculate the number of points that have left? Number of points that have left that have crossed a unit area perpendicular to the motion in unit time is the current. So, I have to just compute the current or the flux. So, that is equal to, if I call this surface S, so that will be equal to just ds, let me just write. So, this V rho, V rho, that is the current, right? I mean, if V is the velocity, so what is the velocity? So, this is, you should remember that this is the velocity in the 6n dimensional phase space. So, there is going to be one velocity component in each of the 6n directions. So, this velocity is just given by, I have written them, q1 dot, q2 dot up to q3n, there are 3n of them, and similarly there will be p1 dot, p2 dot up to p3n, the usual definition of velocity. Okay. Velocity of this phase space point. See, this point you should think of it as a vector in a 6n dimensional space, and the point is going to move to some other point in the next direction, in the next time instant. So, that allows me to define a velocity. What is the net change in what is the net displacement in unit time? That is a velocity. The way we had done it, if you remember in dynamical system theory, I was saying that at every point you can draw a vector field that is going to tell you which direction the point is going to move to in the next instant. So, it is just that, and that has got 6n components, because you can think of it in, like as I said, n could be 1. So, then you have a 2-dimensional phase space, and then one component is x dot, one component is y dot. So, I have done it in the same way, excepting that now my coordinates are q1, q2, q3, and so I put a dot on everyone, and p1, p2, p3n. Okay.
Sir, so system point is moving, but the point of observation is fixed.
System point is moving, but the point of observation. So, what I am doing is that at this point, so this is the center of the, this is my observation point, and I draw a. So, what is going to happen is that some trajectories are going to come in and some trajectories are going to leave this, this unit volume. And what I want to ask is how many points have left and how many points have come in. So, V rho, that is by definition the current, because if V is the velocity and rho is the density, if you remember the usual way of deriving the current, that so there are some particles, let us say the particles are moving like along the direction in which this cross sectional area is there. So, in unit time, only those particles which are contained in this cylinder of length which is v being the velocity, v by definition is the displacement in unit time. So, in unit time, only those particles which are contained in this cylinder of length v and cross sectional area 1, they are going to cross this one. Those which are here, they will not be able to cross, because they will in unit time move from some point to some point here. Only those that are contained in this one. And how many are there in this cylinder? So, the volume of this cylinder is V times 1 by definition, because I want to compute the current, number of particles crossing in unit time in crossing a unit area perpendicular to the direction of the motion in unit time. So, that is v times 1 times rho, okay. That is the general thing, but suppose the motion is taking place in some other direction and you want to know how many particles are crossing a unit area in this direction. So, what I have to do is that I have to take the component of the velocity along the direction in which you have placed your unit cross sectional area. So, that is what I am doing, that if n is the unit vector.
What is the surface element in terms of fields and fluids?
Huh?
Surface element in terms of fields and fluids.
What is, I do not know how to denote. So, you think of points, you know, so in this 6n dimension, so forget about 6n, think of it 2 dimension. So, in 2 dimension a volume is like an area and the surface is the perimeter, you know. So, you just think of it, just generalize it in, so it is the a volume enclosed by a closed surface. So, that is what in 3 dimension think of it as a cube and I do not know what you call the perimeter. Huh? This room itself, okay, this is this okay? How to write it? I do not know how to write surface in terms of maybe there is a we will not need it, by the way. So, I do not know how to write it. Maybe you can, for this one it is like easy, but for in a general.
This is one pair, okay, so that one of that. Volume element is all Q's and all P's multiplication of that. Discard one. Then it becomes
But then you have to take all the possibilities.
So that many surfaces are.
So I don't know if there is a compact way of writing it. Like for 2D it's simple, but
I think the question is like this, that volume element is a general Cartesian dx dy. Surface elements are 3. Dx dy, dy dz and dx dz. Like that. So in this we have so many surfaces.
Okay. Yeah, no, for the general case, like for 2D it's easy, 3D. Acha.
Volume element is this, multiplication of all. Now if you discard one of that, then what is that object?
Acha, so you have to take care of all the possibilities, but I agree. Yeah, that many surfaces, okay. So this is fine, right? So this v is the velocity direction and n is the unit vector, sorry, this is the velocity direction and n is the unit vector perpendicular to the surface. So I want to know how many points are crossing a unit area to which the perpendicular is given by n unit vector. So what I have to do is that I have to take the component of velocity along n. So that is what I have done here, n dot v. So that gives me the component of velocity along the direction normal to the surface and times rho. Okay, and then I integrate it over the whole surface enclosing the volume. So this is the current. So this, I should say, this is a closed surface enclosed. Now you use just the divergence theorem to make it into a, this right hand side into a volume integral, and that will be d omega divergence of v rho. Or what I can do is that I can combine these two terms. So remember that this has been integrated over the whole of the coordinate space. So this gives me just a number that depends on time. So that's why I had ddt outside. But if I bring this ddt inside, I have to be careful to which variable I am taking the derivative. So I have to do del rho del t plus. By the way, this dq dp is nothing but d rho. So that's why, sorry, d omega. Right, d omega is just an incremental volume in that. So d rho del dt plus divergence of v rho, that's equal to 0. Sorry, there is a d omega there. Huh? So there is a minus.
No, it's all there. Put the minus on the DDT, that's fine.
Yeah, okay. It just says that if there is a decrease, that means there has been a net outflow. Some points have come in, but some points have left, and more points have left than those, and vice versa. If there is an increase, then there has been a net inflow. Now this equation, it's going to be true for whatever size of whatever volume element you consider in this phase space. It could be very small or very big, whatever it is. It's just a well, this is just another way of saying that the system is a conservative system, that if you have some volume element, the net volume remains the same. I mean, the number of points which are contained inside that volume is not. So it means that this integrand has to be equal to 0, because it's going to be true for every omega that you consider, and therefore we get this Liouville's theorem that del rho del t plus divergence of v rho is equal to 0. By the way, can somebody tell me how is this divergence operator defined in this 6n dimensional space? So there will be del q1 up to, so this is going to be a 6n dimensional vector, or a column matrix. So del q1 up to del q3n, and then del. So these are the different components. So that's why I put a comma there.
It's very difficult to convince the students, because actually if we think of it in terms of an area under the curve, only when that is independent of the upper limit, lower limit, then it is identically 0 everywhere. So that picture would be very helpful.
So which one are you saying?
I'm talking about this integral d omega. Unless that limit is specified, it is true for all omegas. That's how we say it. So that it is identically 0. The integrand goes to 0. It is brought about by drawing a curve. The area under the curve is 0 only for all possible
the limits.
Then the curve is identically 0 everywhere.
Achha. Okay. Okay, I see.
Now it means that the number of particles incoming and outgoing are equal. Now it is different.
No. It just says that if the number is unequal, in the general case they will not be equal. There may be some specific situations, but if the number is unequal, that is contributing to the local pile up or depletion of the density. See, this is del rho del t. So here QP, rho is changed. I'm standing somewhere here, and I see that as time is passing by, rho is changing. And how is rho defined? I've constructed this small volume around me, and I see that the number is changing. This means that definitely, there has been either a net outflow or an inflow. Net, some points have come in, some points have left. The difference between the two is what I get as the current.
This is also called equation of continuity.
This is called also equation of continuity. So this just says that the total number of microstates doesn't change as a function of time. So I have told you the macrostate, the macrostate is specified by, let's say in this case, the number of particles, total energy, the total volume and so on, and then you list down all the possible microstates consistent with the given macrostate, and as the system is evolving, or as each of these microstates is evolving as a function of time, no new microstates gets created, or no existing microstates gets destroyed.
When we are doing it for charge density, we can physically say charge density. In case of microstates, what is the physical thing that we invoke that it is constant?
I mean, the number of microstates is not changing.
Yes, physically all those microstates are mapping to one particular
Macrostate.
So in that case, what is it that is which is reflected by the fact of the number of microstates. Something like that. Because in case of charge, it's like, okay, there are this many charges.
The way I think of it is the following, that I have told you the number of particles and the volume and the energy, and it's an isolated system. The total energy is not changing as a function of time, and therefore the number of possible microstates is also not changing. It could be that some microstates become more probable, less probable, the density may change as a function of time, but the number of possibilities, okay, think of it this way, think of the spin example. I have told you that you have two spins, and I have two spins, and yeah, so let's look at that. 2 is a bit trivial, so let's say I have two spins, then the possible microstates are, you can list down the possible microstates. It may so happen that some microstates become more likely or less likely, but the total number of microstates doesn't change. I don't know if there is a.
Yes, it is clear because each point moves from one point to the other from time.
It's a conservative system, so that it is a.
So there is no change in the number of those points.
Because, sorry, just one thing, because while constructing the phase space at t equal to 0, I have taken care of all possible microstates. That's how I have constructed my ensemble. I did not leave some of them out. Okay?
No, but in the course of time, the macro is also changing. Okay. So that macro may be consistent.
No, macro is not changing. See, macro is defined by.
We are not in equilibrium.
So there is a distinction. So that's why I said that I will define equilibrium later. Macros is not changing at the level at which I have specified. I have said that the macro. Okay, so maybe this is a good place to tell you what the macro state means in this setting. So the macro state is defined by the total number of particles that the system has, the physical volume in which the particles are moving, and the energy. It may so happen that there is some observable, let's say the net magnetization or something that is there, that may change as a function of time. But at the level of macrostate, I have told you the number of particles and V and E. These are measurable quantities, and these I have specified, and once I have specified these numbers, then you can list down all possible microstates consistent with this given macrostate, and that number doesn't change. It may so happen that there is an observable. I will come to that. How do you define an observable? So this observable is going to be a function of this 6n dimensional space, and that may have an average value that changes and so on, but I will come to that. I mean, don't. So at the moment you forget about making a connection with experiments. The information that I have given you is I have a system of 3n degrees of freedom. The total volume is this much, the total energy is this much. This is the Hamiltonian. Just based on this information, you can construct this picture at time t equal to 0 and at time t equal to 1, 2, 3, 4, etc. at all subsequent times. And what I am doing at the moment is the following, that at time t equal to 0, suppose I had a way to find out what are the possible microstates where they are located. So I locate them in this 6n dimensional space at t equal to 0, and now I know that as time goes by, each of these points is going to move around following these equations, so Hamilton equations. So that's why I have some trajectories going around in the phase space, and then I decided to characterize this picture that there are points distributed at a given time, and each of these points is moving around as a function of time. I have decided to characterize it in terms of a natural quantity, which is this rho QPT.
I understand your suppose we allow V to change, then corresponding microstates will change, or
It will change. But I have said that these are my, if you allow fluctuations in E, so that's another situation. Like here at the moment I am not saying that. I am saying I have given you these values. Like eventually we will see when we go to canonical ensemble that we will allow for fluctuations in the energy. While defining the macro state, I will not tell you the value of energy. I will only tell you the value of the surrounding surrounding atmosphere. Yeah, but this is the simpler situation. I don't know whether it is the simplest of all. That's why it's called. It should have been called canonical, because this is the simplest thing. But I don't know why it is called micro canonical and canonical and so on. Grand. So this should have been micro. I said this should have been cano, and then grand, and then grander. Maybe I don't know what is it. Super grand or something. Okay. So this picture is okay. Right now I haven't made any connection with experiments. How to, suppose you have a measurable quantity, something that can be measured in experiment. How can I interpret such a quantity in terms of rho, q, pt and this space picture? That I haven't yet discussed. I'll do that. At the moment what I am saying is that I have told you the values of n, v and e. And I know that E is a constant of motion, V is also not changing, N is not changing. Therefore, what I do is that at a given instant I list down I make a list of all the microstates consistent with the given macrostate that I call an ensemble, and I know that this collection of points is going to move around. I am trying to characterize that. So, Mustan sir, if I say something terribly wrong or like slightly wrong, then tell me, but this is. No, this Q for a general system, the Q's and P's are they are continuous variables, but there is a situation. So let me, for example, let's say for the spin system, I told you, no, that if you have two spins, and you know what are two spin-off particles, then the total number of microstates is just 4: up, up, down, 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 up, up, down. But for a given energy, only maybe 2 are possible. So that you make a list of those. Let's say I say E is equal to 5 joules. So maybe out of these 4, only 2 are consistent. So you take those down, and they will change as up becomes down, down becomes up, and so on.
In the case of spin, there are n spins. There are 2 raised to n.
2 to the n. 2 to the n. But see, I am so there is another level of. See, I have also told you the total energy of the system. It could be that out of those 2 to the n, so you may have to discard something, because some are, let's say E is equal to 0 or E equal to 5. So depending on the energy, and that I can do because I know what my Hamiltonian is. So I am going to. So I have a bucket of microstates. Let's put it this way: I have a bucket of microstate. Okay, so what I do is that I take one microstate from this, I compute the energy for this microstate. That I can do, because once I have picked up a microstate, I know the q and the p values. So I plug in those q and p values into my expression of the Hamiltonian, and I check if the value of the energy that I get equals the value that I have fed in. If it is yes, then it's like in terms of the indicator function that Mustansi was. If it is yes, I keep it. If no, it's a microstate. It's not consistent, I throw it. So there is an indicator function. We will come to this indicator function while defining the ensemble and the form of rho. You will see that it appears explicitly there. I mean, the fact that you are selecting only a class, only a subclass of all possible microstates for which the total energy is equal to the given value, it will show up.
For spin systems, as you said, it's very clear and discrete. But even for a space, I mean, I thought there was a question on what is the number. So the volume of a space would be an
Yeah, but it's
not a number.
So I cannot count them, like as Professor Mukunda was mentioning yesterday. It's on 1, 2, 3, 4, etc. I know for sure that all the q's would have to lie within this volume V. That I know, but it's not that I can count them 1, 2, 3, 4, 5, or 5. But for a lattice system, when the space is discrete, it doesn't have to be Ising model. Like whenever you have, let's say, okay, let's take the example of the random walk. Random walk. Suppose, okay, so what will be my macrostate? I don't know if there is an energy. So you say there is one particle, and let's say. Okay, so let's say like this. Okay, I have to invoke time, maybe. No, I don't know.
Gas molecules in a box.
So
then your coordinates are continuous, and each gas molecule's position, the configuration of all the gas molecules gives you a microstate.
Both I have to specify the velocities and the position. Yeah, but still that problem remains. I cannot count them on my fingers, right? No, in principle also I don't know how to. These are coordinates which are continuous variables. See whether they.
They allowed microstates in these situations form a continuum.
So you cannot count them. I mean.
To address this question of what are the microstates in the system, how to visualize them, these would be different positions of all the gas.
Yeah, so that's how I have defined them. So that's no. I think the question was, can I count them, or can I count them on my fingers? 1, 2, 3, 4, 5. That I can't do. It's just the fact that these q's are continuous variables. I don't. Is there a so the spin system is one system where the variables are discrete, so I can count them up, down, down, up, or a coin tossing. You know, suppose I tell you that there are 5 coins and the number. So the macrostate description would be the following: that there are 5 coins and number of heads minus number of tails should be something. Let's say A. Now it's for you to make a list of microstates, and there can be many. Okay, coin and spin, the spin up, they are the same. Probably it doesn't. Yeah. So okay, so you are jumping ahead. So at the moment there is no such Planck's constant or anything. Of course, I mean one way to do it is to make a grid, mesh where each mesh, I mean the size of each one is h bar and so. But that okay, that will at the moment it's not there at this level of description. Yeah, sure.
Rho is the density of microstates in the given volume. Right?
Rho is the phase space density. So let's.
The other side, if the surface density.
Surface density. No. So on this side, what I have is I have the current of microstates leave, states which are or points which are leaving that surface. So I don't know how to build up a surface. It's like this, or maybe this one. This is a surface, maybe. I mean, this is a volume enclosed by a closed surface. So if I see that if the amount of water inside has gone down, definitely that means that there has been a net outflow. There must be a leak somewhere. I mean, okay, no, I should not use these words, leak and so on. This will make it like not a closed surface. So forget about water. It's just you have a volume enclosed by a closed surface, and if I happen to observe a net decrease or increase, it could be an increase in the density. If it's an increase, that means definitely more points in the more phase space points in the course of time evolution have come into the volume than those that have left. It's just that. It's like as Shantanu mentioned, I think for charges it's very like, but here also these are charge. You can think of them as.
That rho is volume, phase space volume density.
Rho is phase space.
Domain of integration is surface.
Yeah, and you have to put in this factor of V. V rho is the. And this is J. Okay, so if you want, this is exactly. So that's what I did with this cartoon. That.
ds is the surface bounding that water.
Yes, exactly. Yeah. So how do I compute the current? So what I do is that I go to a particular location. N is the unit vector, and the general velocity direction doesn't have to be along n. So I take the component of the velocity along that direction. And then what I do is that, like the calculation that I did of this cylinder, so this cylinder of unit cross sectional area, right? And so if the velocity is this way, and this is the normal to the unit cross sectional area, only those which are in this direction are going to move away. Those that are going in this direction, that will not contribute. They are going away wherever they are going to wherever they have to go to, but they are not contributing to the current that I am interested in.
It's like crossing a street. I ride my scooty. So I'm going this way, and somebody is walking very fast. Almost parallel to my direction. So effectively he's not crossing.
Yeah, exactly. Absolutely. Yeah. I think this is something that appears in different branches of physics. It's, you have to just identify what are the moving elements. In this case, these points turn out to be phase space points. In charges, these are just charges. When you have some resistance which is connected to a battery, you do a similar calculation. You go to a cross-sectional area and you ask, and then there is, okay, I don't get into equilibrium now because that will be just, okay, so you do the same thing, that there is a surface and things are moving past that surface. It appears in fluid dynamics, in like electrodynamics, it's the same thing, it's just equation. Heat also, heat flux, and the heat equation is, no, probably not. Quantum mechanics also, conservation of probability, this J appears there. I think it is called the equation of continuity in quantum mechanics, so probably this is a name. But it's the same thing, but you have to just identify what is moving, and then it is just telling you that, since it's a conserved system, I mean, you have to also define what is conserved. So here, the number of particles is not changing as a function of time, V is not changing as a function of time, and E is not changing as a function of time. If they change as a function of time, well, this picture will not hold, I have to do something else. If I somehow inject particles into the system during the course of evolution, then this rho will not evolve according to this. All this thing will not. I think probably in non-equilibrium, pK will probably touch upon this. I don't know. So if there is an external drive, for example, let's say I have the system is not closed. I mean, somehow I am injecting particles into the system, or taking away particles, or doing something or the other. Then of course you are creating more and more microstates. So maybe you are destroying. This is not the situation that I am considering. I may consider those situations, but first I have to, I have to walk, learn how to walk before I start running probably. Okay, so yeah, so this part is okay, right? This surface and all this is okay, right? Closed surface, it cannot, okay. And yet this divergence theorem is also and then you can I'll not do those steps. So what you do is that, okay, so you have minus del rho del t, that's equal to divergence of rho, and then so you just expand it out. So sorry, rho v, sorry, rho v, sorry, and so you just expand it out. So you will have terms like del q1 of rho times q1 dot plus del p1 of, let's look at this term in pairs, like pairs of q's and p's. So a typical term will be del qi of rho qi dot plus del pi of rho pi dot, and there will be 3n such terms for every pair of q and p, right? And this, if you expand out, see, there will be one term which is q, so there will be one term, so let me just do it. Okay, so this will be qi dot of del rho del qi plus pi dot of del rho del pi, and there will be two other terms. So this will be del qi of qi dot rho outside and del pi of pi dot rho outside, and you can check that those terms will cancel because I will have to use, if I use these equations, the Hamilton equations, you will get a term del 2h del qi del pi, and there will be a term where the q's and p's appear in the other direction. And so what is this? So now I know what is qi dot. Qi dot is del h del pi, and pi dot is minus del h minus del H del Qi, and if I combine everything together, what I will get is I will get a Poisson bracket. So what I will get is that del rho del T minus del rho del T is equal to, let me just see if I do it correctly. So this is clear, right? I mean, what I did was I just took such terms pairwise for every 3n pairs, and I just expanded it out. So there will be 4 terms. 2 terms will get cancelled because of the see, as Professor Mukunda was mentioning yesterday, you cannot forget about your course on classical mechanics course. You are trying to go beyond classical mechanics. So if you want to go you have to build on that. You cannot forget about now from. So this is something that I see often true with the students. Somehow they think statistical mechanics is something that happens on Mondays and Thursdays between 10:30 and 12:30 when it is taught in the class. Outside those hours, statistical mechanics doesn't apply. Oh, it's something okay. Classical mechanics in Fridays and I don't know, Mondays in the afternoon. Outside there is no class. It's not like that. Everything is there. For a given phenomenon, you have to identify which is the right description that you have to choose to describe what you are after. But it's not that things are just disappearing like in the space of I don't know, physics. I mean, it's not that subjects are being created or destroyed as you go along. They are all there. You have to choose the right one, and then you go and do whatever you want and check with experimental results. I don't know why did I bring that up. Why did I bring that up? So you cannot forget classical mechanics, exactly. Now what is my next point? Okay. Now I have to tell you in this setting, before I come to equilibrium, how in this setting I have to tell you, so maybe I don't need this one. So in this setting, I have to tell you how to make connection with experiment, something that can be measured in the lab. How do I make connection to that? So let's say I have some quantity which will generally be a function of P and Q. You give me the values of P and Q, and I plug those values into the expression that I have of an observable quantity O, and then I get a value. For example, the energy. So I have the expression for, I know what the Hamiltonian of the system is. So you give me the values of Q and P, I plug that into, I insert those values into the expression for H, and I evaluate it. I get the value of O for that microstate. Given a microstate, I know what the value of O is. And what is O? It's up to me to choose, or to, so O could be H, O could be H square, or I don't know, magnetization or something. But it is by definition a function of the Q's and the P's. Okay. So now I define this quantity. So let me go to the other. So let's look at it this way. Suppose at a given instant I make a, or let me do it the other way. I don't know which one is. Suppose I do the following. See, O is a function of P's and Q's. So O is a function of the microstate that a particular point in the phase space. Now it's not that all phase. I don't want to use probability theory, right? Or maybe I have to use. Okay, let me do it this way. That at a given instant, there is a certain distribution of the phase space points on this constant energy hypersurface. Suppose I am asked to compute the average value of O. So how do I do it? What I would do is that, let's say if I am asked to do it on computer. So what I do is that for every microstate, I will compute this value of O, and then I will ask how many microstates are there of this type, and so on, right. So what I will do is that this is by definition, so like let me just write it and then it will be like obvious to you. This is just the definition of, I again write QP, I should write. Okay, now it should be clear. Okay, so what I do is the following. I have this phase space. Sorry. I have this phase space. So somewhere here is my QP, the center of this volume element. This volume element is small enough that the value of this, so first of all, okay, so I have this volume element, and how many points are there in that small volume element? By definition, rho dq dp. It's small enough that the value of this observable for all points which are contained in that volume element is just its value for one point and then multiplied by the total number of points. That's what you do when you do integration, right? That if you choose an interval which is small enough, so then what you do is that you say what is the value of function. So suppose you have a function f of x as a function of x, something like that. So what you do is that you choose a small interval dx, you say what is the value of fx at some point v, so within that interval, so that's fx, and then you multiply it by the interval, assuming that this interval is small enough that the value of function is not going to change over that interval. So maybe I should draw it, I mean it is changing here, so but I have to choose a dx small enough. So dx is by definition an infinitesimal, right, by infinitesimal quantity. So I choose a dx which is so small that the function doesn't change appreciably in that over that interval. So what I do is that so this is my x and this is x plus dx. So what is the value of the function here? So it is just f of x times dx. So that's what I am doing here, that I choose a point and I find the value of O, the observable, at one point here, and I just multiply by the total number of points contained in that. Okay. So that is going to give me the contribution from this small volume element, and I integrate over the whole space. I have to divide out by the total number of points which are there in the whole phase space. And this is, by the way, I forgot to mention, rho qpt dq dp, that's going to give me the total number of points in the phase space. That I can I can normalize rho qpt in such a way that this is 1. Okay, this I can always do. What I can do is that I can call this guy, this to be a new function, rho prime of qpt dq, sorry, dq dp should no. And I can get rid of the denominator. That's what you do in quantum mechanics also, right? You normalize it the way
it becomes a probability.
It becomes a probability distribution. So this is the number of points which are contained in a small volume element divided by the total number of points. That's the definition of probability. Okay. So until now I was using the word I was using phase space density. Now with this definition, rho qpt indeed becomes the probability density. The probability density in this phase space. If I happen to make an experiment, how many times am I going to get this particular point, this particular microstate? But if you think that this definition is, it should not be confusing, but if it is confusing, you can stay with the interpretation as density, and then you have to keep writing this thing. Okay, so now this is going to give me the value of this observable O, the average value of this observable O at a given time. Okay? And that's what I have written here. And of course, this will have a dependence on time, Why this will depend on time? Because rho itself depends on time. So at a given instant, what I do is that I look at my list of microstates, I compute this guy O, I go over this list for every microstate, I compute the value of O and I just take the average. How many are there of this type, that type, and that? Okay, so it should be, it's just a simple average, right? And this would give me a quantity that depends on time, which is the average value of O. It is tempting, and that's what typically is done, is it is tempting to identify this with the observed value of O at a given time. Why it is so? Because at a given instant, from macroscopic measurements, there is no way to find out which microstate you are in. So you say that, okay, I don't know which microstate I am in, but there are these all possibilities and they are all occurring with different probabilities, so let me just take the average. Of course, this is not the only way. You might say that, okay, my macroscopic observable is the maximum of this guy. What I do is that I somehow find this function rho qpt and find where this function is maximized. So then I know that at that time, that is the, those microstates are occurring with maximum probability, and I compute O corresponding to those microstates. But that's not typically done, and let me not get into that. There could be subtle issues where the typical is not the average, and in Carson-Wang there is a small discussion of that, but let me not get into that. Let me just say this way, that it is tempting to say that this is what you observe in experiment, and that's quite, that's quite okay, not just quite okay, actually very, that's actually quite good, I mean very good, because at a given instant if I do an experiment, there is an equipment that measures O, see what I am doing is actually I am measuring the average value. To put it differently, there is like a different way of looking at it. See, when I say I am making a measurement at a given instant, there is no way in which I can, take a measurement at a given instant. Like the best example is you look at our, you look at like, think of our vision, like our, when we are observing something, like our eyes are actually averaging over a small window. So that's so okay that, like over this small window, or you can think of it the way I put, that when you are making measurement, you are actually averaging over all possible microstates at that instant, which is characterized by this. So this is at the level of description or definition. I don't yet know how to compute this guy. What I know is that rho is going to evolve in time according to that equation, del rho del t plus rho h Poisson bracket of rho with h is equal to 0. So that I know. And therefore, in principle, I know how rho is changing as a function of time, and therefore, in principle, I know how does this average value change as a function of time, in principle. So, it's clear, right, where we are getting to? No, it may not be clear where we are getting to, but how far we have been like able to get to till now. This is okay, right? Now it may so happen that let us look at this equation for rho. So I just want to get this sign. So remember how rho is changing. So rho is a function of q, p, t, so this equation in principle tells me how rho is changing. I plug that in, it is telling me how rho is changing as a function of time. Now it may so happen that you happen to reach a state, or the system happens to reach a state in which rho doesn't have any explicit time dependence. Rho has only implicit time dependence. Rho will change because rho is a function of q and p, and okay, so there is no explicit time dependence. If it so happens that rho doesn't have an explicit time dependence, so let's say this you reach a rho that has no explicit time dependence. It may so happen. I am not telling you, I am not giving you a recipe as to how to construct such a state, but suppose you have such a state where the density is not changing as a function of time. Density over this 6n minus 1 dimensional hypersurface is not changing. For example, while the class is going on, as far as I can tell, the density of this room, it doesn't change, right? You are always wherever you are. Here it is very dense, and here it is 0, and there is some dense. The density is not changing as such a state. If such a state happens to exist, then by definition such a state has to satisfy this equation, and therefore that would correspond to a rho that whose Poisson, so the Poisson bracket of such a rho would with h has to be equal to 0 by definition, because I said rho doesn't have to change. So that means rho has to be some function of h. It just tells me this much, nothing more, nothing less. So rho, let me just get to, so rho qp, let me not, so this is some function of h of qp. Maybe why I got rid of this. And if I happen to get to such a state where the rho doesn't have any explicit time dependence, I use that information here. Rho doesn't have any explicit time dependence, so this thing drops out here, this thing drops out here. So then the right hand side doesn't have any explicit time dependence, and therefore the left hand side will also not have any explicit time dependence. So I have been able to get to a state where we have already said that this average is what you measure in experiment. This measured value is not going to change as a function of time. So you would say that, well, according to my definition of equilibrium, the way we have defined in thermodynamics, it's a state in which macroscopic observables, and you will agree with me that this is a macroscopic observable, right? This doesn't refer to one single microstate or 10 of them. It refers to the whole list, whole set of whole ensemble of microstate, collection of microstates consistent with the given macrostate. This is indeed a macroscopic observable, and we will see that the number of microstates, although they cannot be counted on, they are not countably, you cannot count them. The number of microstates is going to increase exponentially with the number of degrees of freedom. At least for one case, it can be. I'll probably not do the derivation, but show you, the result and how it is done. The calculation is not that difficult for a simple system, but like anyways. So this is indeed a macroscopic quantity. It refers to the system as a whole. This is indeed what you measure in experiment. Well, not this is indeed, I mean this is what I chose to interpret this as. There is no one that, and it's a reasonable definition. At a given instant I am unable to make out, and if there is no time dependence here, no time dependence here, and therefore there is no time dependence here. So I ended up in a state where the value of a macroscopic observable is not changing as a function of time, and I would say that the system is in equilibrium. Okay. So this one, the fact that this one doesn't change as a function of time allows me to define equilibrium in the usual way, in the way in which I have defined it in thermodynamics, that it's a state in which macroscopic observables have time independent values. Maybe I will not I think one should say it's a stationary state and so on, but let me not, maybe stationary state is the right way to do it, but or equilibrium. I mean, because equilibrium, the way, there are more conditions involved, but at the moment I think it's just say at the end I'll come. So for the moment forget about equilibrium. Equilibrium just means macroscopic observables have values that do not depend on time. Towards the end, or either tomorrow or let's say in in the next week when P.K. Mohanty talks about non-equilibrium, please remind me or I'll remember to talk about it, that there is a distinction between stationary state equilibrium and non-equilibrium, but for the moment forget about non-equilibrium. This is just and when you have reached such a state where this observable doesn't depend on time, there are many different choices for this rho. So let me call it instead of this tilde, let me call it okay. So it's since I have dropped t, I mean it is obvious that it doesn't have. So there are many different choices for this rho. The only thing that I have to keep in mind is that it has to be a function of the Hamiltonian, because if it is not a function of the Hamiltonian, this guy will not be 0, and that will induce a time dependence, so that will lead to a time dependence in rho. So one possible choice is one in which rho is just constant on the energy hypersurface, that wherever you go, you are going, because that's still a function of energy, that's still a function of Hamiltonian. A constant is, sorry, that's not a function, that is a function. I'll show it in a minute. How does it become a function? Through the fact that this h has to be equal to E. But before that, if rho happens to be a constant, then also rho h, this is 0 and del rho del t is equal to 0. Okay. So this definition of a macroscopic observable is fine, right? And the way we say it is in equilibrium, it's quite natural to do make such a choice. So rho equal to constant is going to satisfy everything that I have said until now. Rho equal to constant is going to give me a value of this macroscopic observable that's not changing as a function of time, and that is going to satisfy this equation del rho del t is equal to 0. Now let's come to what is this constant. I must remember that this QP, this the trajectories, they are moving on the constant energy hypersurface, because total energy is a constant of motion. So then let me just look at my, okay, so when I say rho QP is a constant, what I mean precisely is this thing, and you will at once agree that this is what it should be. It is constant. Well, it's kind of trivial, but let me write. It is constant so long as h of QP is equal to your given value of E, and it is 0 like otherwise. So this is just a reflection of the fact that it is constant, but then you cannot take into account those microstates which are inconsistent with a given macrostate. It's a constant. Constant in what sense? That, like, again come back to that picture of bucket of microstates and you are picking them one by one. So what you do is that you pick a microstate and you check whether the microstate has the given value of energy. Then you keep it, and it so happens that the density of all microstates that you have sampled this way is the same. Then that's that. And it is 0, otherwise this is a trivial statement. It just means that you are not supposed to take care of those microstates which are inconsistent with the given macrostate. You cannot, it is constant, but then you cannot take into account those microstates that have, let's say, 5n particles, or the total energy of those microstates are like let's say 6 times E. So it is constant in that sense, and this you at once see that this would make this this function actually a function of the energy. It is a function of the energy because you pick a microstate, you compute the energy of that microstate and check that its value is equal to E. So that means you are taking care of what the energy of the microstate that you have sampled is. It's not that you are randomly picking all microstates and putting everything into the bag and say, oh, okay, this is rho is constant. So such an ensemble is referred to as a microcanonical ensemble, a collection of microstates consistent with the given macrostate for which the density in the phase space is constant in the sense that I have written down here, is referred to as a microcanonical ensemble. I don't like, as I said, it should have been called the canonical ensemble, but okay, let me not at this stage start defining things afresh. So this is called a microcanonical ensemble. this the concept of ensemble was due to Gibbs. Yeah, this particular, probably it was Gibbs. Yeah, this concept that this, I think it's a very, this is my feeling that at least some of the, I don't know like about like other branches, but generally this is true that these are very deep concepts, but the beauty of these things is that once you understand what they are, you somehow feel they are trivial. And that should be the beauty of them. That once you are, this is just, I could have also done it, something like that. But that's after you have understood everything. So that's the beauty of that. That it's not like even if I or somebody give you 5-hour lectures, and I don't know, I don't have the feeling. I don't have a feeling for it. But now you say, but this is what it should have been. I mean. Okay, collection, I don't know which microstate it is, so I take care of everything. There is a density, the density is not changing, therefore the macroscopic observable has a time independent value, equilibrium, okay, this, so then that's it, it's like that. So I will not do some calculations which are there. So I have a feeling that these things are explained quite nicely in Carson Wong's book. I mean, that's a book that I typically use for teaching, but the other book that some students follow is this book by Pathria, but okay, I don't use it, so let me just leave it at that. So I think the next is maybe at the stage I don't go into the. So when we come back, this was supposed to be a tutorial, but since you did not have questions, so when we come back, we'll do the definition of entropy. Entropy hasn't figured until now. Till now, we have been dealing with microscopics, microstate, etc. And I have taken one step towards making a connection with experiments, in the sense that I have told you how to relate an experimentally measurable quantity in terms of this to this rho, q, p, and microstate, and so on. But as we will see, a significant step towards understanding thermodynamic laws is this connection between entropy, defining entropy, what it is, and making a connection to this microstate, number of microstates, not number, the volume, and so on. So whatever I have done, like, is there a question? Yes. This is like an indicator function. So what you would do is that rho qp, you take care of all the q's and p's, but take only those for which delta. So it's like you take into account all the q's and p's, but then you integrate over all possibilities, but you take into account only those for which your total energy is equal to E. So that's in some sense is going to give you the total number of, not number, but let's say the measure of the microcanonical measure, the microstates which are consistent with the given macrostate. So like as you will see, this delta function, it's really very important, and it becomes a delta function because this h is a continuous variable. It will become a Kronecker delta if you are dealing with spins. Spin is one example, and there could be like others. And like any other question? I think at some point, I mean, what I was thinking was, once you have understood microcanonical ensemble, how things are set up and how do you make connection to different things and entropy and so on, the rest of statistical mechanics, let's say canonical and grand canonical, those things are, I mean, I'm not going to do the usual, derivation and so on. I'll indicate the physical situation that each ensemble is meant to model, and how to go from one ensemble to another. But there are some pretty straightforward calculations, like what's the energy fluctuation in one ensemble, in the canonical ensemble, number fluctuation, and how to do the integral, what's the total phase space volume for an ideal gas, equipartition theorem. Those things I think these things are, you have to just work them. through. I mean, they don't involve. I think it is very important to, as Professor Mukunda was saying this, had said it like over and over again, and I try to say this to my students. It's very important to understand the ideas, the logical structure, and see, mathematics, I mean, that's secondary. I mean, I'm not saying that you have to also master the techniques. I mean, it cannot be that you want to do some microcanonical ensemble without understanding what delta function is all about. You need to have some understanding, but first you have to understand the what you are trying to do, what's the situation. I mean, this understanding of concept and ideas, it's much more important than being able to do some calculation. That you are given a Hamiltonian, blindly what I do is the summation over e to the power minus, there is a tan hyperbolic something, okay, you have to take the root, that's it. So that anybody can do. I mean, not anybody, but okay, some people can do, but that's not what okay, so let me just leave it at that if you don't have any other question. And also statistical physics, or like I think it is true of us, it should not be all about doing simulations. I mean, somehow nowadays I see that you have to basically do some simulation. I mean, let the computer figure out whatever it has to do. I just put in some numbers and that's it, and then I go away, go for a coffee or something, I come back, I plot it, I have a paper, that's it. It should not be. It should not be. I'm not saying, I don't have the authority to say that I cannot stop it from happening, but it should not be like that. Okay. And I wanted to say this while I am being recorded on YouTube. See, one good thing about Ramakrishna Mission is that, and let me say it, because we don't get like anything from government. It's all donation from philanthropic. So I can say certain things. I don't have any obligation to conform to certain. So certain things have to be told, either today or tomorrow, or by someone. So let me make.